I guess today's lecture will be somewhat self-contained. I had, as I wrote over email and on the Zulip, I kind of hoped that I'd be able to follow up what we've been talking about with regards to transformers and also superposition, to be able to really start talking about why attention is important in terms, computationally. But somehow this has been a busy time, so I'm going to put that off for a little bit and talk about something that I understand a little bit better right now. Okay, so what I'm talking about, I'm going to focus on today is a little bit about the geometry, a little bit more about the geometry of ReLU neural networks as a function class, as a parameterized function class. So yeah, just as a reminder, so this is a class, we have neural networks which are parameterized function classes that take the form of compositions of functions of a very particular type between vector spaces. And I'll remind you what that type is in a moment. But for right now, let me just say that anytime you have a parameterized function class for learning, it's important to understand how parameters are related to the actual functions. So, somehow we have parameter space. I'm just going to kind of start with a cartoon. We have parameter space for some function class, and typically in this class I've been calling this omega. So we have our parameter space, but then we also have the actual space of functions.
Ellie, the video got shifted a little bit.
Oh, so is it? Oh, you're right. Okay, thank you. Let me try to make it so that it's more readable. Thanks for speaking up, Caleb.
That might make the other side of the board a little bit short.
Oh. All right, I will do this.
Voila. As a French.
I think that's pretty good. Let's do that. Okay. Okay, so you have parameter space and you have function space. So, and typically this is, you're thinking of this as being functions. So a space of functions from Rn0 to Rnd. Okay, I'm gonna be a little bit more concrete about everything in a moment, concrete and mathematical about everything at the moment. But right, you have parameter space and you have function space. And you might ask, to every parameter, is there exactly one function? And so just as a kind of cartoon example, just kind of as a first example, you think about polynomials. Say single variable polynomials, just to be really concrete. Single variable polynomials as a function class. So let's say PD represents polynomials of degree D. Degree at most D. Well, this is a vector space, and it's the coordinates of the vectors are the coefficients of the polynomial. So you have a single variable x. This is mapping to, say, p of x. But you're representing this polynomial by its list of coefficients. So this is a D+1 dimensional vector space. And in fact, there's a one-to-one correspondence between parameters and polynomials. Okay, so right. I'll say it this way. Is the zero polynomial as an element of the space of polynomials if and only if the string of coefficients is zero. It's the zero vector. So this is pretty familiar. And moreover, there's sort of, you can kind of think of the degree D polynomials as being a slightly more flexible class than the degree D minus 1 polynomials, for example. So, for example, so I'm going to be somewhat informal at the beginning while I'm still motivating things. So lower complexity polynomial classes as measured by the degree. So you might argue with me that degree is maybe not such a great measure of complexity, but I think it's pretty standard. And in particular, if you look at the actual graphs of the functions, you know, degree 3 polynomials, polynomial graphs can have a couple of critical points, a local max and a local min. Whereas degree 2 polynomials, if you look at their graphs, they can only have a single critical point. Okay, so lower complexity polynomial classes as measured by the degree are measure 0. So I haven't really talked about what we talk about when we talk about measure, but for now, just think of when I say measure 0, typically what I mean is that it's lower dimensional. So degree at most D minus 1 polynomials in polynomials of degree at most D sit as a linear subspace. And that linear subspace is the space where the last coordinate is 0. Okay, these are all kind of things that you probably are familiar with. But I just want to remind you about this parametrized function class, because somehow I think that many people might have these kinds of properties in mind when they think about parametrized function classes, that actually the parameters really are functions. And there's a one-to-one correspondence between parameters and functions. But in modern machine learning, this is actually not typically the case. So that's kind of what I want to talk about today, or one of the things I want to talk about today. So here's an informal heuristic. Or belief that's gradually building in the community, is that modern parametrized function classes for supervised learning are highly redundant. And in fact, this redundancy is inhomogeneous. It's often inhomogeneous. So what I'd say is that this first statement, that modern parameterized ML classes are highly redundant, is probably quite well known to the experts. This parenthetical remark might not be so well known to all the experts. At least the experts that I've talked to don't necessarily agree about this. So I guess what I'd like to talk about today is why I believe this parenthetical statement is true, and why I think that it's actually quite important in terms of the dynamics of gradient descent. resolving whether or not this is true is important in terms of the dynamics of gradient descent. Okay, so let me actually remind you what I mean by the dynamics of gradient descent as well. So we've drawn some cartoons of what I call loss landscapes, or what are called loss landscapes already in this class. But remember, you know, if you have a labeled data set for training, so let's call it psi pi I. That is 1 to m. So remember, these are input-output pairs in the input space and the output space, respectively. And this parameterized function class is a bag of functions that you're using to try to predict the y's from the x's. And this is the sort of complete set of possible functions that you're trying to use. And the way that you choose the right function for you is that you have an empirical loss function, some kind of empirical loss function, which depends on this data. Empirical because it depends on the data. And this is now a map from your parameter space to R. And it gives each parameter, or rather the function associated to the parameter, a score. And the score is how well did it do on this training set. So if it's a regression task, then this loss function will be like the mean squared error. The difference between the average of the squared differences between the prediction given by theta and the label given by y. And so that gives rise to some kind of, so now you can draw the graph of this function over omega. And what you're really looking for is minima of this empirical loss. Okay. But the point is that this picture is quite misleading if we really do believe that there are multiple parameters for every function. So in particular, if we know that there are ways of acting on your parameter space to get you new parameters that give you the same function, if you know that in advance, then you know actually that there's some kind of symmetry in this loss landscape, because the loss function depends only on the function, not the parameter, not just the parameter, but on the function. Okay. So this particular point is particularly important, so please ask me questions if that's not clear. So somehow I'm trying to motivate why you would care about ways that you can move your parameter space in order to get the same function. Okay, so I'm motivating this definition, which I'm going to give next, and which, you know, by the way, I'm not sure this, I feel like a lot of this stuff is kind of, in a certain sense, we're building it as we go. So who knows whether this is the right definition, but let me go ahead and give it. So here's a definition. Here's a more formal definition. And I want to state it this way because of stuff that's coming later. Okay, so I'm going to talk about parameterized function classes in a way that really kind of treats as equal, not equal is the wrong word, but on the same level. There's sort of a horizontal treatment of the parameter space and the input space. Okay, so let F be a parameterized function class. Supervised learning. In other words, for training via gradient descent. Well, what would you need this class to satisfy? Well, you probably want it to be continuous. You probably want this function to be continuous. So in particular, F is continuous. And by the way, that will automatically imply that that F theta, which is just what you get when you plug in a particular parameter and you leave the entry for the input open. So now it becomes a map from Rn0 to Rnd. So this map is also continuous. And the evaluation map that you get when you plug in, let's call it EX. F, leave the parameter open and put in an input. And that's a function from parameter space to the output space, are also continuous. And then you also want that it's differentiable almost everywhere, because you need to be able to do gradient descent. So, I mean, one kind of technical point is that you really only need, for gradient descent, you really only need it to be differentiable with respect to the parameters, but let's just impose more, because in practice, we really do often have more. And it makes a lot of other things easier. So I'll say away from measure zero set. Let's see, make F be C infinity, smooth. So all partial derivatives with respect to all parameters and all input points are well defined away from a measure zero set. So think you remove some lower dimensional spaces and you're fine. Okay. All right. So this is what we're working with when we talk about a parameterized function class. And now let me make a definition. A global parameter space symmetry F. So informally is the action of a semigroup so you probably know what a group is. A semigroup, just, you don't necessarily have inverses, but you have an identity, you have group multiplication. Is the action of a semigroup G that leaves all functions Rn0 to Rnd invariant. this is informal. Let me write this down formally. That is it is a non-trivial representation phi. Let's call the representation phi from your group G into let's say smooth functions from the parameter space to itself. So to every group element, sorry, semi-group element, you associate a map from the parameter space to itself. And what do you want this representation to satisfy? Well, you want to satisfy that when it acts on a parameter, it sends it to a parameter that doesn't change the function. So, so such that for all G and G, for all theta and omega, and for all X in your input space. F theta of X is equal to F D sub G of theta of X. Is definition clear? Please stop me if there are any questions. Yeah.
It's a lack of invertibility because injectivity is lost, or is it because some sort of operation prevents it from being inverted?
So it's kind of obvious that if you have a parameter space symmetry, if you have two, usually you can, you know, there's a group operation like that, you can compose them, but you don't necessarily know that you have the, yeah, you don't always, I think it's more that you don't always have a way of getting back.
Like a renormalization flow.
I'm going to give an example momentarily where it's clear that you don't have a way of getting back. Yeah, for ReLU networks in particular, it's just a semi-group that's acting and not a group, fortunately. Okay, so let me start with a warm-up example. So far we've been talking about neural networks. So let me start with kind of the simplest example of a neural network, even simpler than ReLU neural networks. So this is the class of linear neural networks. So let F be well, okay, so I'm just generally going to be starting to talk about parameterized function classes of neural networks. So let's let F be a class of neural network functions. Feed forward neural network functions. Okay, so again, it has this structure. So I'm not yet specifying the activation function. So what I'd like to claim is that you can already see a lot of global parameter space symmetries just from the structure of the computational graph. That's what I'd like to claim today. So of architecture and 0 and 1, etc. through ND. So let's start with this warm-up example. Is that you don't have any activation function at all. So this is just neural network. So it's a composition of affine linear maps. But you're not post-composing with any kind of component-wise nonlinearity. You just have affine linear maps. Okay. So the claim is that there's an obvious action. So no activation function, or sometimes you say the activation function is the identity. So there is an obvious, well, obvious once you see it. It's very obvious. There's an obvious activation, sorry, obvious parameter space symmetry. Global parameter space is global parameter space symmetry induced by an action of GL M1 plus GL and D minus 1. So this action is a change of basis action on each of the hidden layers. Okay, and just to really convince you that this is a global parameter space symmetry, and also to kind of write down some things that are useful computationally. Let me just convince you of this via a kind of more careful lemma. So the claim is that there's an action of the general linear group at each layer that leaves the overall function invariant. And this should not be surprising because, of course, the composition of affine linear functions is just an affine linear function. So this is sort of obviously a very redundant way of representing an affine linear function. Okay, so, but I think that this lemma is useful too, just computationally. So let's let theta be a parameter. For the function class above. Class of affine linear neural networks. Okay, so I just want to be really almost pedantic about this. So for each layer, you have a weight matrix, which I'm going to call W1, and a bias vector, which I'm going to call E1. And I'm going to put them together like this, next to each other, just for the sake of convenience. So, somehow this is the way that we think about the parameters. We might unroll them to put them into we might unroll them to put them into a computer, but this is the way that we think about them. Okay, and let's let X be an element of your input space. Well, then you can define kind of a variant of this. You can define an embedding, sort of a projectivized embedding of the weight matrix and the bias vector into a slightly bigger matrix. So this is just taking care of the fact that these maps are all affine and kind of making them linear in a convenient way. So here I'm just stacking my matrix that has all the information in it on top of just this one hot vector. And let's let X prime be given by stacking X on top of 1. So you're sort of doing this projected embedding. Okay, the claim is that F theta of X, well, it's just X prime times these augmented weight bias matrices. So we just sort of augment all these vectors and these matrices, and then we have a nice linear representation. Of our function. Okay. All right. So I'll leave the calculation. That's an exercise. But now if we want to now understand what the action of this group is on parameter space, well, it's just kind of what you think. And it's actually kind of misleading to write the parameters in this order because we're going to be applying them from right to left instead of from left to right. So so now the next lemma is that if you have an element of this product of general linear groups, then you can act on, I call this phi sub g, phi sub g, sorry, phi sub g1 through g d minus 1. Acting on one of these parameters. Is we're just going to insert a bunch of, you're going to insert G1, G1 inverse, G2, G2 inverse. It's going to look funny when I write it down because I'm going from left to right instead of right to left. So it's Hope I got that right. So I'm claiming that this is a global parameter space. And the proof is you can check by using the previous lemma. So the point is that the GIs and the GLs and the GL inverses cancel. And so it's clear that the function doesn't change. Okay, any questions about that? Yeah.
Say if my parameter space has some other symmetry, say a rotation. So does it help using the training model?
Right, so I think you're asking, is it useful for optimization to use the parameter space symmetries, to use any parameter space symmetries that you have? And the answer is yes. Actually, there's a group that includes Robin Walters at Northeastern and Rose Yu at UCSD, who has and other authors whose names I should remember but don't at the moment, that have used this fact for networks with more interesting activation functions to define something that they call teleportation. So the idea is that you, during the training process, you pick an arbitrary element of your group of parameter space symmetries, and you use it knowing that your loss won't change when doing that. And then you try to teleport to some place with a higher gradient, higher local gradient, and this improves the speed of optimization, gradient descent.
I think there is also a recent work by Jim Halverson.
Who?
Jim Halverson
Jim Halverson, yeah.
on conformal symmetry.
Conformal symmetries.
What are the constraints of conformal symmetry?
So conformal symmetries in which classes? Is it in the data space or in the parameter space?
I think that's symmetry in X.
Yeah.
Symmetry.
Yeah, I mean, it's actually somehow most interesting when you start putting the symmetries together. There, and that's why I kind of want to try to emphasize that the parameter space and the input space are in a lot of ways on equal footing, at least from the point of view of the parameterized function class, and so they should really be treated that way. So yeah, it sounds like these conformal symmetries are symmetries of the input space, and in fact, those have been really well. Yeah, it's been very useful to use those in, for example, developing new types of architecture. So that's kind of the idea behind COMNES, which is that we know that there's sort of a symmetry, at least for the answer that you get for whether or not a picture is a picture of a dog, whether the dog is here or it's here. So the idea is to design your architecture so that that it takes that kind of symmetry into account by defining filters that are translation invariant. And then there's also so something I learned about recently, E3NNs that have been used for biological tasks, because biological objects have Euclidean, three-dimensional Euclidean symmetries, and a lot of things that you might use, you might do supervised learning on in the real world do have Euclidean three-dimensional Euclidean symmetries. So any answer that you give should be invariant under these symmetries. But that again is symmetries of the data space, not the parameter space.
So here we started with the trivial activation function.
Mm-hmm.
And we are still with the trivial?
Right now, we're still with the trivial activation function, and you'll see why in a moment.
Okay.
So I'm starting here because the greatest source of obvious symmetries is coming from the structure of the computational graph. And the point is that the computational graph is kind of based on a deep linear network that you have imposed some extra things on. So now you've imposed that at every layer you insert a composition with a nonlinear activation function. So now if you just look at so this is kind of a perfect segue into the next thing that I'm going to say, which is that if you now look at any sub-semigroups of the general linear group that are invariant, that commute with the activation function, then those will also, that this construction will give rise to those symmetries.
So you're saying that now different activation functions will potentially preserve subgroup?
Exactly, sub-semigroups, right? Okay, so so let's move on to the more interesting example. Which is what we've been studying. So that's the class of ReLU neural networks. So ReLU activation. Works architecture. Zero and one. Here. You know, you sort of largely have the same kind of first lemma. So I'm gonna write down the variant of that first lemma. More precisely, just because it's, I think, useful to know. So lemma. Theta be a parameter, x be an element of the input space. And now for f is above. And now we also have this sign map. So this is going to be so we talked about this at length, but let me remind you. So this is so n is the total number of neurons, non-input neurons. It's 1 to d. And now you're just recording the sign of the pre-activation output of each intermediate neuron. So this is defined to be a sign. This is the vector of signs. I didn't write this down in my notes carefully, so I'm just trying to come up with notation on the fly. But this is a vector of the signs of the pre-activation outputs of each neuron. Let's see, Li is the pre-activation. The ith neuron. Now later. So for every point in the domain, you can write down what its pre-activated sign is for each of the neurons in your network. And remember, this is coming from locating it with respect to the bent hyperplane arrangement, which is giving the decomposition of the domain into these regions on which the function is affine linear. Okay. So this is the pre-activation output of the ith neuron, the elf layer. Okay, and now
So sine is equal to z is 0?
yeah, sine of 0. Yes, exactly, right. So sine of c over the absolute value of c. If c is non-zero, and 0 is 0. See if I can not make a mess of this lemma. So, and W, so the parameters for this network are exactly the same, of the same form as before. So a parameter again looks like W1, D1. W, D. And I'm going to use the same notation as before. So these represent these augmented weight bias matrices, augmented input vectors. Then in this case, f theta of x is one B1 times x. So it's looking a lot like 4, but now you're going to insert these diagonal matrices. And they have ones on the diagonal if the sign is positive and zeros otherwise. So I'm going to call these the indicator matrices for so I'm kind of making up this notation as I go, so I hope it's okay. So for the ELF layer, you have the, you have the corresponding signs for all the neurons in that ELF layer. So this is now a list of negative ones and zeros. So this is the diagonal matrix. This ith diagonal entry is 1 if the sign is positive. +1, and 0 otherwise. So essentially what you're saying, so if the sign is positive, we're saying that the neuron is on there. If the sign is negative, then we're saying negative or 0, then we're saying that the neuron is off there. And so zero. So now let's put in these diagonal matrices. I should have thought through these. in between. In between our half-life linear maps. This is one. It's the first layer. This is the D minus first. Etc. But you see what I'm doing. I'm just inserting these diagonal matrices, which implement ReLU. So you can implement ReLU linearly in this way, which is kind of nice to know if you did it. Essentially what they're doing, and you can convince yourself of this. These are diagonal matrices with zeros and ones on the diagonal. So they're idempotent. Meaning you multiply them by themselves and you get the same thing. You get itself back. That's not really important here, but I'm just mentioning it. But the point is that anything that commutes with these matrices will, anything that commutes with these matrices for all points in the domain will be any sub-semigroup of the general linear group, of the product of general linear groups that commutes with these matrices will therefore commute with, will therefore be a global parameter space symmetry. Okay, so
Why is it ReLU and not a step function?
Oh, yeah, so what it does, what multiplying by this matrix does is zeroes out the respective rows of this matrix and the columns of this, the rows of this matrix and the columns of this matrix. So, so multiplying by this, I guess this is where it's important that it's idempotent. So you repeat it and you get the same thing, and then you see that multiplying by a diagonal matrix like this will zero out the columns where the sign is either 0 or negative. And here it zeroes out the corresponding rows. So the implementation of ReLU is essentially just zeroing out columns and rows in this linear product, but different columns and rows depending on the sign pattern. So the activation pattern is somehow the key gadget here.
So does that mean we're technically squaring all of those matrices and then we just simplified it down in the step that we have on the board?
Yeah, so you can convince, the only reason why it's important that they're idempotent is so that you can quickly convince yourself that when you insert these, they have the effect that I mentioned, that they zero out the column of the matrix on the right and the row of the matrix on the left. The fact that it's idempotent means that you can multiply it by itself, and then you just have to verify what I said for multiplying a matrix by a diagonal matrix with ones and zeros on the diagonal. So yeah, maybe I'll write down some things so that you can verify what I said, or come back and tell me that I made a mistake. But I think I said everything correctly. The only thing I'm not 100% sure of is that it's columns on the right rows on the left, but I think that that's true as well. So, so these matrices are idempotent. So they all have the property that their square is themselves. And is just. Okay, yeah, hold on. I think you have to, I think there is something I said slightly wrong, which is that all of these are augmented, so I think you have to augment these too. Do we have to? But I trust that you can figure that part out. So basically, you know, if everything were linear, it'd be simple to say, it'd be a lot simpler to say, but when we talk about affine linear things, then there's some additional things we have to make sure work out. But the point is that you embed this into a slightly larger diagonal matrix where you just put a 1 at the end. And so let's just say we've done that. And that this is with 0 columns, 0 entries of the non-positive entries. The rows. Sorry, I'm just going to think about whether it's rows or columns. When you multiply by a diagonal matrix on the left, it zeroes out the I think it's the rows. I think it's the rows. Yeah, because multiplying by matrix on the right zeroes out columns. Multiplying by a matrix. Anyway, with the rows corresponding to non-positive indices. And same with the, analogously with the multiplication on the other side. Okay, I've probably beaten this horse too long. So then the claim is that is that products E times D where P is a permutation matrix. E is a matrix non-negative entries on the diagonal. So this is a non-negative scaling matrix. Actually, I want positive entries on the diagonal. D is a diagonal matrix. Positive entries on the diagonal. You with these matrices. These indicator matrices. So what that implies is that what that implies is that you can do the same construction with the sub-semi group of matrices that are products of this kind. That you did before for just deep linear networks. And you get a global parameter space symmetry. So
When you say sub-semi group, you're talking about such PD that are also in GLN.
yeah, these
I
are already in, yeah, right. Yeah, so we're talking about these products in each of the GLN1 through GLND-1 that I mentioned before, exactly.
So they're already all in there anyway. So that's what you meant by sub though, is that that's the larger.
Exactly, yes, yes, exactly.
So PD will implement a different activation.
No, oh, maybe you could think of it that way. That's an interesting way to think about it.
Because this identity matrix implemented by UI.
Yeah,
Right?
yeah, yeah, I'm not sure if you can think about it that way. The way that it's typically talked about is in terms of, so at every layer, so you always have this permutation invariance for neural networks, regardless of the activation function. Because you can always just, it's kind of arbitrary that you ordered the neurons the way that you did. So you always have a permutation, an action of the permutation group. So that's always a parameter space symmetry for neural networks. So in the hidden layers, you can act by permutations. And that's this part of the product. So that's kind of always there. This is often called positive scale invariance. So the idea is that you multiply all of the incoming weights and bias to a node by some positive number, and then all of the outgoing weights from that node by the inverse of that positive number. So that 1 over that, and that preserves the
What it preserves any dimension?
No, just these ones that
ReLU.
yeah, so there's a broader class called homogeneous activations that includes leaky ReLU and some other ones.
So it's a symmetry of some class of.
Yeah, some class of activation functions.
But P is, you said that P is kind of trivial
Yeah, P is trivial in the sense that
for any activation.
it works for every
So
activation
it's
function.
really
That's right. And the interesting thing is that D is a positive dimensional space of symmetries. So in particular, at each hidden layer, you have number of neurons dimensions worth of at least number of neurons dimensions worth of global parameter space symmetries. Okay. Meet with matrices. So the point is that Maybe this is a subgroup. Because it's a group under multiplication, not addition. Anyway, it's also a subsetting group, so let's just keep this. By considering the subsetting group of um, the 10 global parameter space symmetries. ReLU neural networks of all architectures. Same instructions for linear networks.
Matrices of the form above in
Yeah, so generated by products like this.
B and D and
Yeah. So each one of them can be, yeah, each one of them can be written as, yeah, as a permutation times a diagonal matrix with positive entries. But you can take products of them and then get them in this form again. Okay. So great. Okay, so I think that that's a reasonable, at least, introduction to thinking about parameter space symmetries. Now let me make one final definition, and then we'll pick it up again next time.
so the statement is that B and D are represent the symmetry group of value and that's the statement.
I'm not claiming that it's the full parameter space symmetry group,
But
although it probably is.
It is the symmetry.
but we know that it's a, yeah.
It is.
In fact, okay, I'm probably gonna get in trouble for saying this, but I don't actually know of a proof in the literature that this is the full global parameter space symmetry group. Or results about transitivity, for example. Like, when do you get duplicate? Well, I probably just haven't hunted far enough. Probably somebody out there knows that this is written down as the full global parameter space symmetry. But a lot of this stuff is just developing within the last couple of years. So I wouldn't be surprised if there is a full proof in the literature, and I wouldn't be surprised if there is not.
But at least we should know if it's a group. Like,
Oh.
because,
Yeah, no, it is a group. Yeah, it is a group. I was just having a brain fart. Yeah, if you're talking about the positive matrices under multiplication, sorry, positive diagonal matrices under multiplication, then it's a group. Okay, so let me now just give a quick definition of local parameter space symmetries. And that will set me up for next time. So here's another definition. let's let F be a parameterized function class. For machine learning, supervised learning. A local parameter space symmetry. And the semi-group is an action of a semi-group is again, action of a semi-group. That only acts in some sufficiently small ball around the parameter. Space symmetry at particular parameter. It's an action of a semi-group G that acts on an epsilon neighborhood of theta naught. Leaving invariant all functions in that neighborhood. So in other words, there exists an epsilon greater than 0. And a representation from G into the functions on this infinity functions just on this epsilon ball. So this is a representation. And then for all theta in the epsilon ball. All X in your input space. What's the third thing? Oh, sorry. And for all G and G. For all G and G. You want the function to be invariant. So the action of the group is not global, it's just restricted to some epsilon ball. Okay. All right, so I'll leave it there for today, and that will set us up for next time.